I want to do this section on VSEPR and bond hybridization as two separate lectures. So this particular lecture will do the first two parts, which will be the VSEPR theory as well as molecular shape. And then once you kind of absorb that, we can then move on to talk about polar and nonpolar and hybrid orbitals, which won't be too bad. Okay? All right, so VSEPR theory sounds fancy, but it stands for valence shell electron pair repulsion theory. And so if you think of a Lewis structure, a Lewis structure gives us a nice idea about kind of the arrangement of the molecule, but it doesn't tell us about the shape of the molecule. And you may have noticed when you've done your Lewis structures, there are electrons that are involved in bonds, but there are also other electron pairs surrounding certain atoms. And these are defined in VSEPR theory as charge clouds. And they're little clouds of electrons. And those charge clouds will actually repel each other due to Coulombic forces, Q1 and Q2 over R squared, remember that, okay? And so charge clouds, when they are present, are going to repel each other. And terminal atoms then will move as far away from each other as possible because of these. And that will result in very distinctive geometric shapes. And as we go through these examples, these are common molecules that appear on the AP chemistry exam. And often when you see these molecules, you're asked something about the shape of them. So rather than a memorization thing, we're going to just talk about the ways that you can identify and think about chemically what's going on as far as the shape goes. So there's some steps involved in VSEPR theory. So step number one, we're going to count the number of charge clouds. So we'll talk about what that is. We're going to talk, you're going to count the number of bonds. And then, especially in particular, you're going to look at lone pairs around the central atom. So each item in this list is going to count as a single charge cloud. So a single bond is one charge cloud, a double bond is one charge cloud, a triple bond is a charge cloud, one lone pair consisting of two electrons is a charge cloud, and one single unpaired electron. So we will practice this and you'll kind of get, but each of these is counted as a single charge cloud. And then a bond, a single bond, a double bond, or a triple bond is considered one bond, and a lone pair consists of two electrons or a single unpaired electron. It is not likely that you will be asked to predict the shape of a compound that has a single unpaired electron. So we're not going to worry about that. So there are 13 shapes that we will commonly come in contact with, and the first few probably 85% of the time, and then the others about 15%. So when we talk about bond angles and things, that's where this comes up. Okay, so let's talk about two charge clouds. Carbon dioxide, two charge clouds, okay. So VSEPR theory, there's two bonds. Let's take a look back here. And we're looking at the central atom, not at the oxygens on the outside. So there's a double bond here and a double bond here. Each of them count as a charge cloud. There are no lone pairs around the central atom. So there are two charge clouds, there's two bonds. All right, no lone pairs. The shape of that is linear. All right, linear geometry. There are two charge clouds around the carbon atom, and 180 degrees is as far apart as the terminal atoms can get from one another. So the two charge clouds repel one another as they are both negatively charged. So this is as far apart as these can get. And so just to go back and take a look at that, again, we're looking at the central atom, all right? 2 charge clouds and no lone pair, all right? BF3, okay? Now, remember, boron is our example of an incomplete octet. And if you remember why, boron only has 5 protons, and so it can't handle 8 electrons. So this is our incomplete octet, and we're looking at the central atom. You should see a charge cloud here, a charge cloud here, and a charge cloud here, and no lone pair of electrons. And so if we have 3 charge clouds, and it's 3 bonds with no lone pair, the shape is called trigonal planar. Trigonal planar, and our most common example of trigonal planar that you'll see over and over and over again is BF3. Now, you could also have BCl3, BBr3, BI3, any of the halogens. Most commonly, though, you will see BF3. So trigonal planar, and you're going to work with an online simulation where you're going to get to build some of these molecules, and you'll be able to kind of see this. So the bond angle of a trigonal planar is 120 degrees. Something you may find helpful is to just make yourself either a single sheet where you'll kind of make a chart of the different bond angles and the different shapes, or make yourself some note cards where you kind of go through this. So another example of 3 charge clouds, so there is more than one way to be 3 charge clouds, is the NO2 minus polyatomic ion. All right, so nitrogen is our central atom, and so there's a charge cloud here, there's a charge cloud here, and there is a lone pair of electrons up here, which is considered to be a 3rd charge cloud. Okay, so this is the nitrite polyatomic ion, and it has 3 charge clouds. 2 of them are bonds. 1 of them is a lone pair. So notice the shape is not trigonal planar, but rather it is bent. And ideally, in trigonal planar, you will have 120 degrees, if you remember. But we see less than 120 degrees in this structure because the lone pair sits a little closer to the nitrogen atom than the bonding pairs. And that kind of pushes, these guys a little closer to each other. And so you do not need to know what the bond angle is, but you do need to understand that because of the presence of this lone pair, why the bond angle in the case of NO2 minus is less than 120 degrees. So a question from College Board would probably be, the bond angle for BF3 is discovered to be 120 degrees. The bond angle for NO2 minus has found to be less than that. Discuss a reason why that might be. And it's because, and always look for the presence of that lone pair, okay? All right, 4 charge clouds. Most common example we see is methane. So you notice around that carbon there are 4 charge clouds, and so the shape for 4 bonds with no lone pairs is tetrahedral, and the bond angle for tetrahedral is 109.5 degrees. So right now we have 3 bond angles to remember. We have linear at 180 degrees, we have trigonal planar at 120 degrees, and now we have tetrahedral at 109.5 degrees. Ammonia. Notice we have 4 charge clouds, but we have 3 bonds, but we have a lone pair. And so, would you predict the bond angles in ammonia to be greater or less than those in methane? If we have 4 charge clouds, 3 bonds, 1 lone pair, we now have trigonal pyramidal, because that lone pair of electrons is going to push those 3 bonds kind of closer to one another. The shape of the charge clouds is still tetrahedral, but the shape of the molecule is trigonal pyramidal. So although the shape of the charge clouds is still tetrahedral, the bond angle between the terminal atoms is reduced because the lone pair is going to sit closer to the central atom than the bonding pair of electrons. So the lone pair, these guys right here, are going to repel the bonding pairs with more force, and that's going to cause the terminal atoms to move closer together. Therefore, the actual bond angle is less than 109.5 degrees. Another way to have 4 charge clouds is to have 2 bonds and 2 lone pair of electrons. And so we have 2 bonds and 2 lone pair, and bent. Over and over and over and over and over again, you are going to see the bent molecule because it is water, okay? This is going to be a different bent, all right? We have 4 charge clouds, we have 2 lone pairs. Our other bent, if we go back here, where did we bend? We bent somewhere. This bent, okay? This bent had 3 charge clouds, so it only had 1 lone pair. Okay, now with water, we're going to have 2 lone pair. And so here are the 2 lone pair, okay? And so we have 4 charge clouds, so the ideal bond angle is 109.5 degrees because it's 4 charge clouds. But there are 2 lone pair repelling the 2 bonding pairs. And so the 2 lone pairs in water sit much closer to this oxygen and to the central oxygen atom than the bonding electrons. And so this increases the force acting on the bonding pairs, and it causes these to move closer together. And so water, common example. All right, 5 charge clouds. If you remember, everyone 3p and high in the 3p orbitals and higher can have expanded octets. And so this is phosphorus pentachloride. And so the shape of someone with 5 bonds and no lone pairs is trigonal bipyramidal. And so this one has a trigonal planar geometry, and then it has a terminal atom coming off the top of the central atom at 90 degrees and off the bottom of the central atom at 90 degrees. So trigonal bipyramidal. Another way you can have 5 charge clouds is to have 4 bonds and a lone pair. And the shape of 4 bonds with a lone pair is considered to be seesaw. So we're going to have a seesaw shape. And in the seesaw shape, all molecules with 5 charge clouds, trigonal bipyramidal, are going to lose terminal atoms from the trigonal planar part of the structure. So the bond angle here, the ideal bond angles are 90 and 120 degrees. But you will get extra force on the bonding pairs, which pushes them together because of this lone pair of electrons. So while the ideal bond angle for this part is 120 degrees, we're going to be less than that. And our ideal bond angle of 90 will also be less than that. Another way to have 5 charge clouds, this one's a crazy one because you have 3 bonds and 2 lone pairs. So iodine trichloride is another compound that can have an expanded octet. The 5p subshell is very close in energy to the 4f subshell. So here, iodine has 2 lone pairs attached to it, and you'll actually get a T-shaped molecule. So this is what a T-shaped molecule looks like. And then we have xenon difluoride. Oh my goodness gracious, look at this. Okay, so we can take our trigonal bipyramidal, but think about what we're going to do to those ideal bond angles when we have 3 sets of lone pair electrons. So let's just go back. All right, so here it's actually because of how those electron pairs can push those molecules, we actually end up linear. And that's because of the 3 lone pair. 6 charge clouds, SF6, sulfur hexafluoride. VSEPR theory, 6 bonds and no lone pairs. We have octahedral. In an octahedral molecule, it's kind of like putting together 2 tetrahedrals, sort of octahedral. So all the bond angles are 90 degrees. So you could attach 8 flat triangular faces to this structure. And so each of these faces would connect to 3 terminal atoms. And if you did this, you'd make an octahedron. Thus, we say it has an octahedral geometry. So in octahedral, all bond angles are 90 degrees. And so if you bring out 6 charged clouds, but you have iodine pentafluoride, think about that octahedral of 90 degrees. What are you going to do to those angles then, those ideal angles, when you add that extra pair of electrons? And so that shape is actually said to be square pyramidal. And so the lone pair repels a little more than the bonding pairs, and so the angles are a little bit less than 90 degrees. And then xenon tetrafluoride, it has 6 charge clouds, but this time we have 4 bonds and 2 lone pair, so that shape is considered to be square planar. And so this is a square plane. It has lone pairs of electrons above and below the plane. So 1 lone pair above and 1 lone pair below the central atom. All right? And so that's the last of the shapes that you need to know. And again, just make yourself either some flashcards, just kind of go through the shapes. And so understand for each of the charge clouds, 2, 3, 4, 5, and 6, understand what the ideal bond angles are. Also, understand what the shapes are for those who end up having some lone pairs of electrons, and understand then that those bond angles are going to be a little bit less than the ideal one with no lone pairs of electrons. If you have compounds that have multiple central atoms, you're going to look at each atom on its own and count the charge clouds and bonds around it and predict the shape around it. And then you isolate the next central atom and you repeat the steps. And so it says predict the shape around each carbon in this molecule. So I don't think, yeah, you do. Okay, good. All right. Okay, so predict the shape around each carbon atom in this compound. And so here's our carbon number 1. We have 3 charge clouds, right? And no lone pair. So what kind of geometry do we have? We have, that's right, trigonal planar geometry, right? Okay. Then our second one has 2 charge clouds, right? And so you will have linear geometry. And then our third will be back to trigonal planar again. All right? So look at the first part of the homework that goes along with this and practice predicting some shapes. I'll continue on with the second lecture where we'll talk a little bit about hybrid orbitals and things, but then we'll have a lot of opportunity to practice with this. So guys, thanks for following along with this. You can watch it as many times as you need to kind of get those shapes down. So feel free to email me or message me and let me know what questions you have. Thanks, guys.